Hey there, college algebra. All right, we're rolling on section 5.2 inverse functions. I've got the bullet points on the board there for you. So the key word I want you to see, though, not only inverse, but functions. So remembering that for a function, there has to be for every x, one y. Okay, so we want to remember that. We can't have two outputs for one input. So just remembering the property of a function. What's our reminder on what a function is? So for every x or input, there is exactly one y or output. Okay, a little light there. Better marker. Okay. So we want to just keep that in mind as we're working these, because we're only finding inverses that are going to be, that need to be functions. All right, so let's go ahead and get started here and see what we're talking about. So if I graph x cubed, this was one of our basic graphs that we talked about before. Okay, there's x cubed. I'm going to go ahead and give you what the inverse is. Now, I'm going to call it g, but there is a symbol that we use for the inverse function. And the inverse of x cubed is cube root of x. And we're going to look at this graph. And the graph of cube root of x looks like this. Okay? Now, looking at them separately is fine. We can look at them. We're going to plot some points and analyze the points, but then there's another way to compare them. So these right now, these are inverses. They're inverses of each other, and they are inverse functions because each one is a function. Okay, each of these are x cubed is a function, and cube root of x is a function. So now let's look at some points. So if we wanted to plot points here, the most common ones we would maybe do is -2, -1, 0, 1, 2. And I'm going to cube each of those, right, to get the output. So we cube -2, we get -8. We cube -1, we get -1. We cube 0, we get 0. Cube 1, we get 1. Cube 2, we get 8. Even we could do 3, and we would have the point 27. Obviously, I can't plot that. It would be way up there, but we get the idea there. Now, what's important to look at here, when I go to do the chart for cube root of x, it's not going to make sense for me to use -2 if I want to do this without a calculator, because I've got to go and do the cube root of -2. And we know cube root means what? Cube root means what number can multiply by itself 3 times, right? That's what we're looking for. So this is a decimal. It's not going to be easy for us. So it's better on this type, it's better to pick numbers that are themselves cubes, okay? So instead of picking -2, how about I pick -8? Because -8 is a perfect cube. -1 is a perfect cube. 0 is still considered. 1, 8, 27. And so if I do that, cube root of -8 asks what number multiplies by itself 3 times, we would get -2. Cube root of -1, -1. Cube root of 0, obviously, is 0. Cube root of 1 is 1. Cube root of 8, what number multiplies by itself 3 times to give 8? That's 2. Cube root of 27 is 3. Now, if you take a second, I'll stand in the middle here. You can see, look at these ordered pairs and look at these ordered pairs and see what you notice. Okay? So specifically, this has the point -2, 8. This has the point -8, -2. All right? Of course, the -1 and -1, you see those. But look again here, 2, 8, 8, 2. 327, 27, 3. Okay? So And on all of them, I mean, it's the same. It's harder to see here because the input and output are the same. But what are we comparing? What is it that you see on the points, the coordinates here and the coordinates here? Well, let's just do one more. So if we do 4 cubed is 64. So then I'm going to take the output there, 64, and the cube root of 64 is 4. And that's going to always happen. So on inverse functions, the inputs and the outputs switch. Okay, that's a key, a component key property of inverse functions. So if AB was a point here, then BA must be a point on the inverse and vice versa. Okay? So a key property of inverse functions is that the easier way to say it, of course, is with x's and y's, but it's inputs and outputs. The inputs and outputs switches from one function to the inverse function. So the inputs, which are the x, and outputs, which are the y. Make sure you can see it. Switch from one function to the inverse function. All right? And the symbol we would use then, so since we see that this happens, if we want to call this, if we want to call cube root of x the inverse of f of x, then I'm going to change the notation. And we would use this. We would put an f with a -1 and then put the x there. So that means it's the inverse of f, or it's read f inverse of x. Okay, that's how it's read. F inverse of x means it's the inverse of f of x. So you can use that notation. All right, just running out of a little room here. Erase this definition for now. And so for the property, one main property that we can see that we'll put, so properties of inverse functions. If AB is a point on f of x, then BA is the corresponding point on f inverse of x. Okay, that's an important property. So let's just track these two and see what I'm talking about here. So for instance, 2, 8, 1, 2, 8, somewhere up here. This one has the point 2, 8, okay? So the inverse of f should have the point A2, which we discussed, all right? But it's kind of hard to kind of recognize what this means when we leave them separate. So what I'm going to do is I'm going to take the inverse function and graph it on the same graph so we can compare. And I'll do that one maybe in a, let's see if we can use a lighter color, and this pink will hopefully show up here. So I'm going to graph f inverse here on the same one. Okay, so this is f inverse. Okay, yeah, we can see that it shows up. And what it means now, when I'm saying the corresponding point, means that there's the line y equals to x would go kind of right through here. It's not, I didn't draw that the best. But if we could draw the line y equal to x, these two graphs are flips about it. So if I flip about y equal to x, I should get the other graph. So what we mean by the corresponding point is if I flip that point to here, that should be the point A2, okay? And that's what we mean when we're talking, when I've mentioned that if we have 2A, we have A2, it's the flip about the line y equal to x. So if we put both functions on one axis, that their graph should be symmetric about y equal to x, okay? So I'm going to add that. We're running out of a little room now, so I'm gonna need to make some erases. So let's go ahead and do that, and then we can all right. So the other property I'll put is that for inverse functions, their graphs are symmetric about y equals to x. So we'll just keep a mini view here. This was f for this problem. This was f inverse. And when we'll put them together, we could see the symmetry there, okay? Those are just rough sketches, all right? So now we've listed some important properties of inverse functions. But now, one thing is this: not every function has an inverse that's a function. Okay, so what I wanted you to think about for just a second: what function, if I switch its x's and y's, or flip it about y equal to x, will then give us something that's not a function? So it may not be that easy to think of off the top of your head, but the easiest example I can give you is, say, f is x squared, okay? So you start off with this. We've got our parabola, and we'll make a little t-chart here. So -2, -1, 0, 1, 2, that's 4, 1, 0, 1, 4 on the points. If I put the line y equal to x through here, like this, and we flip this about, we flip it about the y equals to x, it means it's going to kind of tilt your head diagonal. Our inverse should look like this. That should be the inverse. But notice, it's not a function. Because if we look at the points now for f inverse, we know that all the x's and y's should switch. So now if I look at the points on this, it should be 4, -2, 1, -1, 0, 0, 1, 1, 4, 2. So just looking right here, at the point 1, we have an output at 1 and we have an output at -1, not a function. At 4, we have an output at 2, we have an output at -2. So you can see that the inverse is not a function. So the inverse of x squared is not a function, but it's really came to start with x squared. There was an issue with x squared. And the issue with x squared is that x squared itself is a function, but the fact that these 2 points here, these 2 points, if we track this point, 1, 1, -1, 1, we have different x's with the same y. And what we use to see that is called the horizontal line test. So what we can see with x squared is that since x squared, I can draw a horizontal line that goes through 2 points. That's then going to lead, when I flip, to this vertical line that's going to go through 2 points. So the problem is that x squared, we say, is not 1-to-1, okay? And you can write the numbers 1-1. I just wrote the words out. So it needs to be 1-to-1 so that its inverse would be a function. So for instance, when we look over here, if I draw a horizontal line through this graph, it never intersects more than once, okay? It just intersects one time. So then when I go and get the inverse function, notice that this is a function. It passes the vertical line test, okay? So this is the easiest example to give, is usually is to see it with a parabola. So with a parabola, we can see it's not 1-to-1, okay? So in order to be 1-to-1, what has to happen? So to be 1-to-1, for every x, there is 1 y, and for every y, there is 1x. So you can replace that with input output. So for instance, another example of something not one-to-one. All right, we take absolute value of x. All right, it's this picture. Notice it fails. That was supposed to be a horizontal line. So it fails the horizontal line test, because if I draw a horizontal line, for it to be one-to-one, it can only cross once. And this is not one-to-one because for the y value, whatever you want to call it, say this is the y value 2, it has two inputs, 2 and negative 2. So for every y, in this case the y value 2, there could only be one x. Easiest way to say that is it must pass the horizontal line test. So it must pass HLT. Means if I draw a horizontal line, it can only intersect once. Okay? And if we wanted to see what the inverse would look like, the inverse is this. This is the inverse graph. Thus, it's not a function because those 2 points are going to flip and we're going to have this picture here. Okay, so that's what makes it's the easiest to see with a graph. So if you can just graph and have a look, that's the easiest way to see if something's one-to-one. So to be one-to-one must pass the horizontal line test. What's horizontal line test means? Horizontal line test means that a function is one-to-one if a horizontal line, if any horizontal line only crosses the graph once. If crosses more than once, it's not one-to-one. Okay, so that's our definition of one-to-one. If we go back to our bullet points here, we've got our basic properties, our definition of one-to-one. Okay. So now, given a one-to-one function, how do we find? So this is the bulk of your lesson of what you're going to be doing. So how do we find it? If I'm given a function, how do we find the inverse function? So let's get started with that process. And I'll do a couple of problems and I think you'll see it's pretty easy. Okay? So we'll call this example 1, given a function, let's say a one-to-one function because we want its inverse to be a function. Given a one-to-one function, find the inverse function. Okay. All right, so let's start. So part A, f of x is 4x plus 2. There's our function, okay? So the first question is that one-to-one? So at this point now, I'm hoping that you have got to rely on previous knowledge and previous topics that we've discussed. So when we look at this, we can see this is linear. You can graph it in 2 seconds. Y-intercept is 2, slope is 4, so it goes like this. So look at that. Does that look one-to-one? If I draw a horizontal line, is it ever going to cross twice? No, so it's one-to-one. So this is good. So now the question is, how do I find the inverse to this? How do we do that? So I'm going to replace f with y equals, and write it like that. So what was the main thing that we saw before? So the main thing, the main property or the main characteristic was what happens with your x's and y's, right? The x's and y's on one, then switch and become the y's and x's for the other one. So basically what we're going to do, the first step, when we want to find the inverse is we're going to switch all x's and y's. So we're going to switch all of them, okay? So I'll write it x equals 4y plus 2, okay? So that's the first step. And then I'm going to just solve for y. Okay? So, all right, so we've switched x. Wherever I saw y, I put an x. Wherever I see x, I put a y. And now I'm going to solve. So I'll do subtract 2 from both sides, and then divide by 4. And so we get y equals x minus 2 over 4. And that should be our inverse function. So we can label it as f, or we can label it as f inverse of x. And so here's what I'm going to do. I'm going to test a couple of points to see if that's really true. So I'll go back to our original, and let's see. So, and here's the problem or the answer that I found. So let's go back to f. So let's test a couple of points on f. So for f, we can see it has the point 0, 2, right? This is a point on that. I can see it right there. That means here that for this has to have the point 2, 0. The x and y have to switch. So let's see if that happens. So if I plug in a 2, f inverse of 2, we get 2 minus 2 over 4, 0 over 4, which is 0, check. All right, just to do another one. If I plug in a 1 here, we get 6, 1, 6. That means here, this has to have the point 6, 1. So let's see. F inverse of 6, 6 minus 2 over 4 is 4 over 4, which is 1, check. So there are inverses, okay? And that's the process for if you're given a function, how do you find the inverse? That's how you do it, okay? We'll do another example. All right, I'm going to move for a second. Obviously, you can rewind the video and come back to this, okay? So I'll go ahead and erase. You can pause if you're still taking notes. All right. So let's do the x cubed that we did earlier, and then I'll do a variation on x cubed. We'll do, say, x cubed plus 2. All right, we'll work those two and just see if we can find those inverses. Main thing is, remember, is the starting function 1 to 1? So that answer should be yes. We've already seen this. So I'll go to the side. I'll make it y equals x cubed. I'll switch x and y. X is y cubed. So the question is, how do you solve for y? All right, that's the second step. Well, you got to take cube root of both sides. Cube root of the left and cube root of the right. And what do you get for cube root of y cubed? Cube root of y cubed is just y. And there you go. And was that the inverse that we worked with at the start? Yeah, that's f inverse. Okay, and we go to the next one, part C, and so we'll save this. So again, I'll make this y equals x cubed plus 2. I'll switch x and y. X is y cubed plus 2. Okay, and let's see. So we'll solve for y. So now I'll subtract 2, and then I'll take cube root of both sides. So cube root of x minus 2 is cube root of y cubed, which is y. So for this one, you got f inverse to equal cube root of x minus 2. And again, how could I check? Like, so for instance, real quick, this looks like it has the point 1, 3. If I plug in a 1, we get the output 3. That means this has to have the point 3, 1, which it does. Plug in a 3, 3 minus 2, 1, cube root of 1, 1. Okay? All right. So now one more problem here. Remember, we've studied piecewise. So if I do part D here, if I give you this, believe it or not, that has an inverse function. F of x is x squared, x greater than or equal to 0. Once I put this little constraint, that means just x squared only to the right of 0. And when I look at this, it is 1 to 1, passes the horizontal line test. So if I want to find the inverse, I'll make it y equals x squared, right? then I'm going to switch all the x's and y's. So wherever I see a y, I put x. Wherever I see an x, I put y. And notice I even did it on this restriction. Now, on the inverse, y has to be greater than or equal to 0. And so what that means is, normally when I would solve an equation, I would do plus or minus square root. Well, I don't want a negative answer because all my y's, it says the y's have to be greater than or equal to 0. So I do square root of x is y is greater than or equal to 0, and that should be the inverse. So let's see, does that make sense? If I graph this, I got that picture, and notice that they're symmetric about line y equal to x. That would be the inverse, okay? The last thing real quick is, how can we prove that they're, so I give you two functions. Let's take the first two that we did. I think we got what, 4x plus 2, and then we got x minus 2 over 4. How can we prove? So to prove, because the x's and y's switch, if we do f of f inverse, or vice versa, we should always get the answer x. If you get that answer, then they're inverses. So I'll take the first two. I'm going to do f of f inverse, and then in this case, it's x minus 2 over 4. So that means I'm going to do composition, which we learned in the previous section. This is going to go in here in place of x. So we're going to get 4 times x minus 2 over 4 plus 2. And we're going to work that out, and we should get the answer x. 4 is canceled. I get x minus 2 plus 2, which is just x. There you go. And that's a way to prove that two functions are inverses. I know it's the board's a little mushy here. We got a lot going on. So let's just prove the original two that we did. Right here, I'm going to prove that they're inverses. So the x cubed and the cube root of x. So you do composition. One goes into the other one. So if I do f of f inverse, that means I'm going to do f of cube root of x. That means this will go in here in place of x. So it would be cube root of x cubed. All right, well, what happens when you cube a cube root? You cube a cube root, these basically cancel, you get x. Okay? And they're inverses. All right, so in this lesson, we looked at properties of inverse functions. We looked at the definition of one-to-one. You know that given a one-to-one function, how do we find the inverse? That's where we switch the x's and y's, solve for x. And then this is the proof. You do the composition, you should get x. Hope this helps. And this wraps up lesson 5.2. Okay, good luck.